Welcome back to our class, Module 4.4, Redox Reactions. Let's continue Module 4.4, Redox Reactions. We'll look at oxidation number. We'll look at an illustration for that. We'll look at how we can balance redox reactions. We use illustrations. We'll look at reduction potentials, uses of reduction potentials. We'll look at illustrations, the probability of a reaction, and we'll make some conclusions. Oxidation number. The losing of an electron or losing of electrons by an atom attended by an increase in its oxidation number is called oxidation. Also, the gaining of electrons by an atom attended by a decrease in its oxidation number is called reduction. Remember when we looked at the Daniell cell, we said that the zinc is oxidized because the zinc loses 2 electrons and turns from zinc Zn to Zn superscript 2 plus. That means the oxidation number of zinc at Zn is 0, but the oxidation number of Zn 2 plus is plus 2. So there is an increase in oxidation number from 0 to plus 2. And that's why we say the zinc is oxidized. The same thing for the copper in the Daniell cell. The copper Cu2 plus has an oxidation number of plus 2. When it accepts 2 electrons, it turns into Cu, which has an oxidation number of 0. So there is a reduction in the oxidation number from plus 2 to 0. And that's why we say the zinc is reduced. So oxidation reduction can be described in terms of loss and gain of electrons, respectively. Therefore, in redox reactions, the oxidation number of one or more elements in the reaction species changes. Now, in the Daniell cell we looked at, you see that the oxidation number of zinc increased from 0 to plus 2, and that of copper reduced from plus 2 to 0. So you have an oxidation, you have a reduction reaction, and when we combine the two, that is what we call reduction oxidation reaction, and for short we use redox reactions. Now we have some rules. Free elements such as atom has an oxidation number of 0. That's why we said zinc oxidation number is 0, copper oxidation number is also 0. So free elements, their oxidation numbers are 0, e.g. hydrogen, sodium, sulfur, phosphorus, all has oxidation number of 0, and so on. So many of them, all the free elements, their oxidation numbers are 0. The second rule, in simple ions, that is ions containing one atom, the oxidation number is equal to the charge on the ion. This is exactly why we said zinc 2 plus, the oxidation number is plus 2. Cu2 plus, the oxidation number is plus 2. Also, Al, aluminium 3 plus, the oxidation number is plus 3. Barium, Ba2 plus, calcium 2 plus, the oxidation numbers are plus 2. Cl minus, the oxidation number is minus 1. So, and so on. So for simple ions containing one atom, the oxidation number is equal to the charge on that ion. Now there are specific or special rules. So we have elements having constant oxidation numbers in compounds. So there are some elements that have constant oxidation numbers in compounds. For example, alkali metals, their oxidation number must be plus 1. For example, potassium is plus 1, sodium is plus 1, so the oxidation numbers must be plus 1. Now, metals of the subgroup of group 2, examples of metals of group 2 like zinc, like cadmium, their oxidation numbers must be +2. Again, hydrogen exhibits an oxidation number of +1 in all of its compounds, except in metal hydrides, such as sodium hydride. You see, now in sodium hydride, sodium, which must have an oxidation number of +1, if hydrogen now has oxidation number +1 again, then there won't be anything like sodium hydride. So in sodium hydride, sodium will now force hydrogen to have an oxidation number of -1, while sodium will have an oxidation number of +1. The same thing happens calcium hydrides, we say metal hydride. So in any metal hydride, the oxidation number of hydrogen will change from +1 to -1. All oxidation numbers must be consistent with the conservation of charge. Now, conservation of charge is something as law of conservation of energy or law of conservation of mass. Energy is neither created nor destroyed. So in conservation of charge, it means that if you have an equation, if you have a net charge on the left-hand side of +2, you must have a net charge on the right-hand side of +2. If that is not so, then it means that your equation is not balanced. What you have as a net charge on the left-hand side must be the same as the net charge on the right-hand side. So we'll go ahead. Neutral molecules, the oxidation number of all atoms must add up to 0. So, for instance, what you said about sodium hydride, sodium has +1, nitrogen has -1, +1 minus 1 is equal to 0 for sodium hydride. That's what we mean. So for every neutral molecule, for instance, sodium chloride, NaCl, oxidation number of sodium is +1, oxidation number of chlorine, the chloride there is -1. So +1 minus 1 will be equal to 0. If it is not 0 for neutral molecules, then whatever calculation you did is wrong. Complex ions. What we call complex ions are ions made up of more than one atom. For example, if sulfuric acid is split or dissociates, you have the hydrogen ion and the sulfate ion, that is SO4 2-. Now, SO4 2- is a complex ion because sulfur is there, oxygen is there. So for complex ions, the oxidation number of all the atoms must add up to the charge on the ion. So what we're saying, for instance, SO4 2-, if you look at the oxidation number of sulfur, look at the oxidation number of 4 molecules of oxygen. If you add it, it must be equal to -2. That is the charge on that complex ion. But of course, we're going to look at some examples. The oxidation number of oxygen in each compound is 2, except in peroxides. You see, the same thing that happened to hydrogen is happening to oxygen. It has an oxidation number of +2, except in peroxides, where its oxidation number is -1, and in oxygen fluoride, where its oxidation number is +2. So we're saying that the oxidation number of oxygen will always be -2, except in peroxides where it is -1, and in oxygen fluoride where it is +2. Now we'll have illustrations. The first question is saying, find the oxidation number of sulfur in H2SO4. Now you imagine H2SO4, we're looking for the oxidation number of sulfur. So we'll go back to our rules. Oxidation number of hydrogen is +1. Oxidation number of oxygen is -2, as we said in the last slide. So for H2SO4, we have 2 molecules of hydrogen. So let's assume that the oxidation number of sulfur is X. We don't know it. And we said for neutral molecules, H2SO4 is neutral. So for neutral molecules, it must be equal to 0. So we have hydrogen is 2 molecules, plus 2 times 2 will give us 2, plus X. X is the oxidation number of sulfur. Oxygen oxidation number is -2. We have 4 molecules. 4 times 2 is 8. So we have 2 plus X minus 8 equal to 0 because it must be 0. H2SO4 is a neutral molecule. Therefore, when we solve that, X will be equal to 6. In fact, that's why the IUPAC name of sulfuric acid is tetraoxosulfate 6 acid. So that sulfur, the oxidation number is 6. That's why you have that tetraoxohydrogen sulfate 6 acid or sulfuric acid. So the oxidation number of sulfur is X. Now, example 2 shows us that we can also obtain fractional oxidation numbers. Now, what is the oxidation number in sodium thiosulfate? Sodium thiosulfate is Na2S4O6. The same thing again. Let the oxidation number of sulfur be X. So for sodium is +1 times 2 molecules will give us +2. Sulfur is 4 there, so +4X. Oxygen oxidation number is -2. We have 6 molecules. 6 times 2 is 12. So we have +2 plus 4X minus 12 equal to 0. When we solve that, we have the oxidation number of sulfur as equal to 5/2. The next example is what is the oxidation number of chromium in dichromate ion, where we have Cr2O7 2-. Now, this is a complex ion. The charge on that complex ion is -2. Remember the rule that says that the total oxidation number for complex ions must be equal to the charge on that complex ion. So let the oxidation number of chromium be X in Cr2O7 2-. So chromium is, of course, we have X, we don't know, that's what we're looking for, but there are 2 molecules there, so we have 2X minus 14. Oxygen is -2, 7 molecules times 2, that's 14. So we have 2X minus 14 equal to -2 because the charge on this complex ion is -2. So when we solve, 2X will be equal to 14 minus 2, which is equal to 12. So we have X equal to +6. That's the oxidation number of chromium in that compound. Now, balancing redox reaction. There are 2 situations when we are in acidic solution and when we are in basic solution. Now, all these follow the same procedure except for just a little difference between the 2 acid-basic solutions. The first thing to do is to write a skeleton equation indicating the reactants and products and identify the elements whose oxidation numbers change in the reaction and find the oxidizing and reducing agents. Once you're able to do that, then you're good to go. You separate the change into half reactions. You must have half reactions. Know the oxidation half reaction, know the reduction half reaction. Now you balance each half reaction separately. Now in balancing these half reactions, these are the things you do. Change coefficients to account for all atoms except hydrogen and oxygen. Add water to the site deficient in oxygen. Add hydrozonium ion or hydrogen ion to the side deficient in hydrogen and an equal number of water to the opposite side. Add electron to the side deficient in negative charge. Then we'll multiply half reactions by appropriate numbers needed to balance electrons. Then we'll add the 2 half reactions. Subtract anything that is on the left and the right will cancel out. And you have your balanced redox reaction in acidic solution. When it is in basic solution, then it must not contain hydrozonium ion or hydrogen ion. So what we now do is, in order to add hydrogen, remember There's the third step there. We said add hydrozonium ion or hydrogen ion to the side deficient in hydrogen and an equal number of water to the opposite side. Now, because we don't want it to contain hydrozonium ion, we now replace that step by adding water molecules equal in the amount of deficiency of hydrogen, then equal number of OH on the opposite side. We don't want it to contain hydrogen ion because it's not acidic solution. So the rest of the rule is the same for acidic solution. Okay, let's look at an example. We're going to balance a redox reaction. We have MnO4 minus giving us Mn2 plus 4H2O. If you look at that now, you see that on the left-hand side, right-hand side is not equal. So first rule, we add hydrogen ion on the left. And since we have added hydrogen ion on the left, we'll now check which side is deficient in electron. We'll add the electron. It is the left-hand side. We have added this electron. Now, if this above reaction is between the manganese ion and iodine, the above is the half reaction for manganese ion. Now, for iodine, we have 2L minus giving us L2, 2I minus giving us I2 plus 2E. In order to obtain the overall equation, look at for manganese, we're having 5 electrons, whereas for iodine, we're having 2 electrons. So we must have the same number of electrons transferred. So we multiply the iodine equation by 5 to get 10 electrons and multiply by the manganese equation by 2 to get 10 electrons. And that's what you have here. We now add and get the last balanced equation. If you check this equation, it will be balanced both by charge and by atoms. Another example between bromine and ion 2 ions. We are following the same thing again. This is the reaction for bromine, reaction for ion 2, oxidizing from ion 2 to ion 3. We'll look at it. How many electrons is transferred? So we need to double the Fe2, Fe3 plus equation so that we have the same 2 electrons. And we add the 2 and get the overall cell reaction. Redox potential. In the Daniell cell, electrons are given to copper ions at the copper electrode, which are thereby reduced to copper. The same effect may be produced if we replace copper electrons or copper electrode with another electrode. Now, from an external circuit, the same thing we have said before, we're just trying to lay emphasis. So we see a solution, assuming we have replaced the copper with iron, we see this equation. Therefore, it is possible to have the same metal ions dipping in concentration solutions, and that will give us what we call concentration cells. We are going to see that later. So we are just using this slide to lay emphasis on the standard conditions I mentioned earlier. pH must be 0, temperature should be 25 degrees C or 298, and concentration of both the oxidized and reduced form must be 1 molar. Uses of redox potentials. We can use redox potentials for a lot of things. One is to find the oxidizing and reducing power. Remember, I talked about the activity series in the last module. So if the half reaction changes from reduced form to oxidized forms, electrons will be liberated, which means powerful reducing agents are reduced species of half reactions with highest negative values, e.g. K, calcium, potassium, sodium. On the other hand, powerful oxidizing agents, so we can use redox potentials to find oxidizing and reducing power. And we'll give an illustration here, displacement of hydrogen by metals above it in the series. That's what I said, activity series. There are metals above hydrogen and there are metals below hydrogen. Those metals above hydrogen will have negative EMFs or standard electropotentials, while those metals below will have positive electropotentials. And that's the illustration 4 we have here. We can also use redox potentials to find the probability of a reaction. And we have used illustration 5 to show that by combining with Gibbs free energy, standard Gibbs free energy, we see that delta G naught is equal to minus NF E naught. N is the number of electrons, F is the Faraday, E naught is the standard electropotential. So we can see that when the delta G naught is negative, the reaction is spontaneous. Without calculating the actual values of delta G, we can see that a positive E naught will give a negative delta G naught. And that means the reaction will be spontaneous. So we'll see how we can use E naught and delta G naught to predict probability of a reaction. Thank you very much. We'll come to the end of this module. I hope to see you in the next module. Thank you and God bless you.